Hello there. In this lesson, we're going to learn about strong acids and bases. And so the operative word there is strong. So strong means that the degree to which the acid or the base ionizes or dissociates is very high, as in 100%. So when you have a strong acid, 100% of the acid molecules will ionize. And if you have a strong base, 100% of the basic ionic compound will dissociate. So whatever the concentration is that you mix up here will be the same concentration of hydroxide ions or hydrogen ions that you have on the other side. One way to represent the strength of an acid or base, and we're going to focus on acids here, is to use a percentage. And for acids, it's the percentage to which it ionizes. So we'll start with a couple examples here. We have HCl, good old hydrochloric acid. And it is a strong acid, which means 100% of those HCl molecules will separate into hydrogen ions and chlorine ions in the solution. With a weaker acid, like vinegar here, or acetic acid, it forms an equilibrium where the hydrogen ions will separate and then reattach at a given rate. And you'll have a much lower percentage that actually stay as hydrogen ions in solution. So that's the difference. A strong acid will always be 100% ionized, where a weak one will be much, much lower. And so you can show that with a basic percentage. Just divide the concentration of the hydrogen ions by the overall concentration of acid molecules that you had to begin with, and multiply by 100 to make a percentage. So let's start with a strong acid. Since we know that the percentage ionization of the strong acid is 100%, and we know that the concentration of my acid here is going to be 0.05 moles per liter, and we know times 100, the concentration of the hydrogen ions then is going to be, if you move this all over to the other side, you'll end up with a hydrogen ion concentration of 0.05 moles per liter, which means the pH is just the negative log of that, 0.05 moles per liter, and you'll end up with a pH of 1.3. Great. So now we have a weak acid, and this time we can't assume 100% because it's weak, and we're given the percentages, and it's only 2%. So 2% is what we're given for the percentage. Same concentration of acid, so I'll put that down here, 0.05 moles per liter. We want to know what the concentration of hydrogen ions are times 100. And so what you end up with is the 2% divided by 100 times the 0.05 moles per liter will give us the hydrogen ion concentration. And if you work that out on your calculator, you'll end up with 0.0001 moles per liter for the concentration of hydrogen ions. And if you take to get the pH of that, you're going to do negative log of the 0.001 moles per liter, and that comes out to a pH of 3. So there you go, pretty big difference. Same concentration of acid, but the strong one is going to have a lower pH, and the weaker one will have a higher pH because not as much of it ionizes. Okay, so let's go the other way and see if we can figure out which one is the strong and which one is the weak one. So it says, what is the percent ionization of an acid that has a concentration of 0.001 moles per liter and a pH of 3? Well, we got our relationship down here, so we need the concentration of hydrogen ions, which we can get from that, right? So our hydrogen ion concentration is going to be 10 to the negative 3, and that's going to be 0.0010 moles per liter. So I think you can see where this is going. The percentage then is going to be the concentration of the hydrogen ions, which is 0.001 moles per liter, over the concentration of the acid, 0.001 moles per liter, times 100. And of course, that comes out to 100%. And that means that this is a strong acid. Yay, ding, ding, ding. Now, you can probably see where this one is going too. but just to make sure that we can go through the math of it, let's figure out the concentration of hydrogen ions here. It's going to be 10 to the negative 5, which is 0.00001 moles per liter. And then the percentage here is going to be the hydrogen ion concentration. Got the 4 zeros and the 1 moles per liter on the top, and the concentration of the acid, which is here, 0.025 moles per liter times 100. And this one works out to be 0.04%, which means this one definitely is a weak acid. So it turns out that the number of acids that are strong is pretty low. There's only 6 of them that are very commonly used or that you'll see. And if you remember those ones, then all the rest are going to be the weaker acids that make the equilibrium, and that'll be more of the focus for the rest of this unit, of course, because it's an equilibrium unit. So getting to know the strong ones is really helpful. And there is a memory aid that I found that I'd like to share with you here. And the way it works is, so I brought no clean clothes. And so the S is for sulfuric acid, the I is hydriodic acid, the Br is hydrobromic acid, the No is nitric acid, the clean is hydrochloric acid, and clothes is perchloric acid. And so if you can get used to those 6, then any other acids that you see, you'll automatically know are going to be the weak ones. Okay, so let's have a look at some of these acids and see if we can help make sense of why some of them are strong and some of them are weak. You might have noticed that 3 of the acids all start with hydro, which means they are binary acids, and they are all in the halogen column here of the periodic table. And so if they're in the same column, that means that as you go down the column, you're adding layers of electron shells. And the reason why they're pretty acidic, or on the strong side, is that the further that hydrogen atom is from the halogen nucleus, the easier it is to pull it off. And then the final one, the smallest one here being fluorine, because it's so small, the attraction between the hydrogen and the fluorine is large enough that this makes hydrogen fluoride a weaker acid than the other 4. And the hydrogen does not come off 100% for that one. So the trend is, as you go down a group of binary acids, the bond strength decreases, and that makes the acid strength increase. You have a stronger acid when the bond strength is weaker. So now let's look at some molecules that are binary, that are potentially acids in the same period or the same row in the periodic table. We'll use this section here just as an example. And we'll have a look at these molecules that should be familiar to you. You've got methane and ammonia and water and hydrogen fluoride. And so the main difference there is going to be the electronegativity of that central atom, with carbon being the least electronegative and fluorine being the most as you go across that section. And what happens is carbon and hydrogen have pretty much the same electronegativity, and that makes that bond pretty much non-polar. Nitrogen is quite a bit more electronegative, and so you end up with a polar bond here and here and here. Oxygen, again, a lot more electronegative. Here and here are going to be polar. And then fluorine is the most electronegative, and so this is going to be the most polar. So you're going to have most polar here and pretty much non-polar here. And so the more polar your molecule gets, the more acidic it will be too. Acidic. And that's because it means that the electrons are being pulled away from this hydrogen here, and it makes it easier for it to come off when it's in solution and make the solution acidic. We already know that water does this on its own as well. These water molecules will release hydrogen ions as well, and that's what puts it at a pH of 7. Ammonia, not as acidic again, and so the trend is going to be from least acidic to most as you go across a period here. So our next group is our oxyacids, Of course, oxyacids have oxygen in them. And we're going to compare oxyacids because they all have the hydrogen attached to an oxygen. So the only difference then is going to be what the central atom is for an oxyacid. And so, of course, the central atom is going to have variations in the amount of electronegativity it has as well. And the general trend is that the greater the amount of electronegativity, the more polar this bond between oxygen and hydrogen will be. So this here is going to be your most electronegative of the three here. And that means this bond will therefore be the most polar, which means this is going to be your strongest acid. And over here you have the least electronegative of the bunch, which makes this bond the least polar of this bunch, which makes this the weakest acid of this bunch, right? So you can just follow that trend if you remember your trends off the periodic table. The more electronegative, basically the closer to fluorine you are, the more electronegative the atom will be, and the greater that electronegativity means a more polar bond and a stronger acid. So the final thing to consider here is what is the effect of adding more oxygens with your oxyacids. And so we've got the variations on chloric acid here. Hypochlorous acid only has one, of course, and so there's a certain degree of polarity due to the attraction of the oxygen and to the chlorine, that both are going to attract the electrons in this bond and give it a certain amount of polarity. If you remember, the more polar that bond, the stronger the acid will be. So adding another oxygen makes this group here more electronegative, and it makes this bond here more polar. So that means that this guy here is going to be stronger of an acid than the previous one, right? Chlorous acid will be stronger than hypochlorous acid. And the trend continues. As you add more oxygens, now we got this whole blob all attracting the electrons in this bond here between the O and the H, and that makes it more a stronger acid than the chlorous acid, right? And finally, perchloric acid, which is one of our strong acids at 100%, has the electronegativity of all four oxygens plus the chlorine, all drawing electrons away from the OH bond, and makes this easier to come off and makes this the strongest of these acids. Yay! All right, lastly, let's consider the bases that are strong. An example here would be lye. Lye is sodium hydroxide, and if you use it as a drain cleaner, little crystals might be inside here, and you put them in your drain, and then they dissolve and dissociate. 100%. They completely dissociate and become hydroxides in solution, which makes it a base. And all of your metal hydroxides from group 1 and 2 will do that. There isn't any equilibrium to worry about except for the one that's with water. So once hydroxide gets into the water, of course the water has an equilibrium that's producing hydroxides and hydrogens as well, and it'll interact with that. But these compounds themselves, as long as the concentration is low enough, they'll dissociate 100% and be your strong bases. So keep an eye out for metals of group 1 and 2 with hydroxides. Those will be your strong bases. Okay, I hope that helped. We'll talk to you soon. Bye.